I thought it was just. Yeah.
I actually remember my
Oh, wait, sorry, like,
only because they're getting the ones in.
You said it was.
I think on the boys always moved together. Yeah, and then we go to kiddos going around. Yeah. It's not. We have one great locally and have like way better stories.
What?
Man, you should have been on back. Yeah, but while in my year, my year would be the morning, and then that straight ones in my.
Oh, yeah.
You just wrote up.
Could do that.
My career was, my full on career was in high school, but it started February 25th.
Well, I just never know.
It makes sense to figure out what's great up. Look at that thing. Thanks.
For like unusual.
That stuff, yeah.
But they're met, right? They're all met.
If you go home.
Okay. Is there any?
Like this.
I just remember the all shutting up.
Yeah, they're like this.
Okay, I hope that we can get through this packet by the end of this week. So these are BC topics up to polar. So today I'd like for us to review integration by parts, linear partial fractions and proper integrals, and maybe we can get to Euler's method as well. And then tomorrow we'll do logistic models, arc length, vector value functions, and then I hope that on Friday we can just focus all of our attention on polar area. And then we should be able to, get through hopefully most, if not all, the packets by Friday, or by the time we get back from break. Okay, so integration by parts. Here's the formula. It's kind of like a reworking of product rule, but with integrals involved. It's kind of like a rearranging of it. So integral of fg prime is equal to fg minus the integral of f prime g. There's also another method, which is using tab method. And tab method allows us to work through these problems when you have these nested integration by parts. But typically, those are going to be a better fit if you're f, or if there's no natural log involved, or if it's like x squared e to the x, or x squared x squared like sine of x. Those are going to be the best fits. Integration by parts are going to be good fits usually when you have two different families of functions that are being multiplied together, and you're asked to find the integral, and then you just can't quite get a u substitution to fit the problem. So this is kind of like a workaround for problems that your u substitution is not able to get going. So it says function f has a continuous second derivative. The table above gives the value of f and its derivative f prime as selected values. What is the value of the integral from 1 to 2 of x f double prime of x dx? And we can already tell that u substitution is not going to quite get us there, right? I mean, if we do u substitution, we're going to get u f double prime of u, and that's not going to allow us to make much progress. So what if we can think of one as f and the other as g prime, and we go through our integration by parts steps? So I'll let the f be the x, and I'll let the g prime be the f double prime. Now, on the f side, we're going to be building the derivative. On the g prime side, we're going to take the antiderivative. So we're going to make them go in opposite directions here. So f prime is equal to 1. And then g is going to be f prime. And now we're just going to be pairing them together in this form here. So it's going to be fg minus the integral of f prime g. Now, when you go through when you start with your integration by parts process, you have one portion that's going to be complete and the other is going to be incomplete. So just know that when you go through that process, there's always going to be a portion that we have to still finish up. So x f prime is done. We just have to worry about the integral of f prime. And we can make f prime rise up to what? What's the integral of f prime? Just f, yeah. So we're left with x f prime minus f of x. Okay, and now what can we do? We have the antiderivative. Now we can do what? Plug in the bounds. Okay, plug 2 in first. Then follow it up with 1. And then use your table of values to get your answer down to a number. Sometimes I like to use this acronym to help me remember what the order of priority is in terms of, what's going to be the f. Sometimes you look at two expressions, you don't know which one do we assign to be the f, which one is going to be assigned to be the g prime. And so this the priority order is that if you ever see a log or natural log involved and you want to do integration by parts, your log always has to take on the f variable, and the other is going to take on your g prime. So in this case, we have natural log of x. We have a polynomial. Natural log of x is going to win out. It's going to take the priority. So you will let f be natural log of x, and then you will let your g prime be the polynomial. All right, try those steps. See if you can step through the process like how we did number 1. why do we not have to worry about plus c with definite integral? Right. Plus c will just wash out. Integral of fg prime is equal to fg minus integral of f prime g. And when you step through building out your integration by parts, you know there's always going to be a completed portion and the incomplete portion. You still have got to do a separate integral process even after your fg minus integral of f prime g. And we get to that f prime g, we just have to do some cleanup, go through multiply 1 over x through, get my terms ready for power rule, apply power rule, then plug in my upper and lower bound. Okay, once we're done with 2, we're going to go to page 2, number 4. Start looking at some linear partial fractions. So number 4, page 2, you're trying to find the integral. Typically, we know partial fraction can be part of the process, especially if you have a really kind of a condensed expression, numerator, denominator. It doesn't quite look like U substitution can get us there. But you look at your denominator, and it feels like your denominator can be nicely separated into individual fractions. So that's when we can kind of tell, you have all these linear factors that are being multiplied. So if we can get them into the sum of smaller fractions, then we should have an easier problem to solve. So that's the goal here. We would like to get this into the form of a over x plus 2, b over 2x minus 1, and c over 1 minus x. Because if we can get it into that form, then the integral of each of those individual terms hopefully should be ideally just easy, hopefully relatively easy natural log individual rules, 1 over u du's. But we have to first figure out how to assign that a and b and c value. So I go through what I call the cover-up method. We find the factors that we want to work with. So in this case, my factor is -2. And I'm going to go to my original fraction. I'm going to cover up my x plus 2 and replace my entire remaining expression with -2 and see what I get. I'm going to get -8 minus 14. And my denominator is going to be -5 times -3. Sorry, let me see, 2 times. Sorry, -30 over -15, and I get A is equal to 2. Next up, 2x minus 1. If I set that equal to 0, I get x equals to 1/2. Hover up the 2x minus 1 and replace every x with 1/2. It's a little messy, but ends up giving us b equals -4. And lastly, for the 1 minus x, cover up the 1 minus x, replace every x with 1. I get -3 over 3, which is a -1. So we now have 3 individual problems. You don't have to separate with separate integrals. I just want to show that these are really just individual problems that we can all handle using use substitution. Now, these are all relatively easy problems, but we do have to be careful about what? Okay. What else? Okay.
-6.
All right. What else? We got to go through use substitution. You may be tempted to feel like, oh, every problem will be like this, just natural log of x plus 2. But I remember on the test or on the quiz earlier in the semester, sometimes we overlook these types of denominators and it feels like, oh, that's just natural log of 2x minus 1. No, but we got to go through use substitution. There's going to be some leftovers that we don't see with x plus 2, right? X plus 2's derivative is 1, and we don't have to worry about that there's any leftovers here. But there are leftovers here, so you do want to take the time to go through a full use substitution, even though you know it's going to fall under that natural log umbrella. Okay, any questions there? Try number five, we can work with that denominator, right? Get that denominator, factor it out. You can see the product of two linear expressions and split them up. Okay. Any questions with 5? This one, if you can recognize, oh, my u value is my derivative, it's not going to produce anything other than 1, you can skip u substitution, but always take the time to look at your denominator. Even though you know it's natural log, sometimes the derivative may produce something that you don't expect. So don't assume that every denominator is not which is produce a derivative of 1. And for number 5, we're having to match the answer choice, and the answer choice is using quotient property to merge those log terms together. It gets it into that form of natural log of A minus natural log of B can be condensed into natural log of A over B. Okay, next up. Let's go to the next page, and let's explore improper integrals. So improper integral is if one of your bounds is sitting at infinity, or one of the bounds is sitting at an asymptote. We'll go through a lot of the same process. It's just that at the end, our evaluation is, would be either approaching the vertical asymptote or our B approaching infinity or negative infinity. So let's start with number 7, page 3. So this looks like maybe a normal problem, but we can see that the reason why there's improper integral here is because if I were to insert -3 in for x, right, this graph is basically undefined, right? At -3 it's undefined, so we know that there's an endpoint that's undefined, and we have to basically involve the fact that we can approach -3 from the right side of -3, but we're not going to be able to have anything right at -3 because there's a vertical asymptote at -3. But we're still going to go through the same process like we normally would, right? And if you saw an integral problem, let's say you didn't see the bounds there, what process would you go through? Not for integral problems, use substitution, yeah. So we'll handle the integral portion first, and then we can worry about the bounds. But we know this is going to be U substitution, most likely a power rule problem. You can either bring that x plus 3 up now or wait till you do U substitution to bring it up. But either way, we got to go through U substitution. This won't work with natural log. So we know that we can't be right at an asymptote, but we can approach the asymptote on the right side of -3. So we can say limit as b approaches -3 from the right side of -3. And then our antiderivative here is -2 over x plus 3 to the 1/2. Evaluated between b and 0. And when you evaluate the bounds, you're just going to plug in numbers like you normally would. And let's see what we get. -2 over 0 plus 3 to the 1/2 minus -2 over b plus 3 to the 1/2. Oh, sorry, this should be -8, right? -1/2. And now, if we explore this a little bit, I mean, we can't plug -3 in. We're going to get 0 undefined here. But if I were to plug in a value slightly less than -3, let's say -2.9, -2.9 plus 3 or -2.999 plus 3, what's going to happen to my denominator? Well, that denominator is getting smaller, right? Which means that the overall value is increasing to infinity. So if one piece goes to infinity, the whole thing breaks down, right? We know that our answer is going to diverge. All right, we're not able to produce a real number because my fraction isn't decreasing to 0, it's going up to infinity. So it doesn't matter that this is a real number. If one portion is diverging, the whole thing diverges as well. Part B, we can obviously tell that this is also improper integrals. But look at this xe to the -4x. Anyone know how we can approach what method is involved to find the integral here? Right. Integration by parts. Right. Now this one doesn't have natural log. What's a method that we probably would prefer with integration by parts if we can do it? Yeah, we like to use tab method, especially tab method are good if you have a polynomial paired with exponential or polynomial paired with trig. Those are really good places for us to take advantage of tab method. So we'll take the antiderivative there, and then we can worry about the bounds for b approaching infinity. So this is also good practice for us to see that tab method. So not good for natural log, but it's good for polynomial versus exponential, polynomial and exponential. So we start off with f being the x and the g prime being e to the -4x. On the left side, we're going to keep finding the derivative until we get to 0. On the right side, we're going to keep on taking the antiderivative until we reach the same number of times that the left side took to get to 0. the integral of e to the negative 4x. A little bit of u substitution. What's gonna come out of u substitution with that negative 4x? Negative 1/4, yeah. If you know that pattern, you don't have to go through a full u substitution, but just want to show that it is negative 1/4 each time we take the antiderivative. And it's a little gimmicky. A couple of things we have to remember. We're always going to start off with a positive sign, negative and positive, and then you're multiplying the diagonals with starting with the upper left corner. So positive x times negative 1/4 e to the negative 4x. Minus 1/16 e to the negative 4x. And then we can evaluate this between 1 and b. The nice thing here is we are going to get a converging answer because the infinities in the denominator we see as b approaches infinity, both these fractions will go to 0. So that zeroes out, and that leaves us with our real number answer. Okay, I want to make sure I get to Euler's problem here. So if you can turn to page 5. Oh, sorry. There should be an X here. Sorry, I lost that X.
Hey, is she here?
Yes, thank you.
Thank you.
Yeah, sorry. When we move by the diagonal, the X does remain. But the b over e to the 4b, we still get that denominator growing at a fast rate in the numerator, so this still zeroes out. So yeah, sorry, I lost that X when I was going through that method. Okay, page 4. So with Euler's method, we're kind of using linear approximation to kind of work our way through. So with Euler's method, whenever I like to start off just by creating my table and then just kind of work my way through. So here are your details for your table. You're going to start off with x, y sub 0, or y prime, or dy dx, or f prime. And then you're basically are just going through your linear approximation step. Y is basically y equals mx plus b, or y is equal to y minus y sub 0 equals m times x minus x sub 1. But it's going to be y is equal to y sub 0 plus m times x. That's kind of like, yeah, that's basically point slope form. So number one, it says if dy dx is 2x minus y, and if y equals 3 and x equals 2, use Euler's method with 5 equal steps to approximate y when x equals 1.5. So we also need to figure out delta x, because delta x is b minus a over n. I saw this issue on I remember this issue on the quiz where we do have to be careful about our delta x. Sometimes your delta x ends up being positive, sometimes it ends up being negative. It depends on which direction we're going. So if we're starting with a higher number and ending with a lower number, then we should be expecting our delta x to be negative. So, so just be aware of that. So in this case, my a value is 2, my b value is 1.5, and my n value is 5. Right, I'm starting at 2, I'm ending at 1.5. So just be aware. So I saw issues where students forgot or didn't think that delta x could be negative, and that threw off a lot of their answers because they're putting in a positive number for delta x in their process. So in this case, delta x is negative 0.1. So we can start off our table this way. Start at 2 and go down by negative 0.1 until you reach your destination. And then step by step, you're just going through and gathering your y value. And once you get your y value, you're going to update it and let that be your next values to plug into your dydx. Yeah, BC Topics, yeah. And typically, if this shows up, it's in the calculator section. So 2 goes in for x, 3 goes in for y. We get 4 minus 3, which is 1. That's our slope. That's our delta x. Y sub 0 plus m times delta x, which is 2.9. Update, go to your next row, create your new y value, and then repeat the same process. And then we're going to end once we get the y value associated with 1.5. Okay, so your homework, pages 1-8. I'll send out a reminder this afternoon. Homework, packet 2B, pages 1-8. All right, come get your phones.
Okay.